Hi, Taylor. Those were some brutal antiderivatives that he gave you. I've uh, I've written out for you so that you can read through them, and I thought it would just take too long for me to do a video where I was having to write every step out. So I wrote the whole solution out for you for those last ones that we didn't finish on Thursday. So here's the first one, and we had already gotten a bit of a start on this. The substitution is over here that you have to do for the by parts. And we got down to the part, I think about here on Thursday. And I was thinking it was one of those ones where you cross out on either side, but it's not. It's if you, because we've got the same thing here and here, then I'm going to bring this term over to the left-hand side and it will change to add. So I'll have two of them now on the left-hand side. And then if I bring that 2 over and divide it into the right side, it leaves me with the original integral equal to that all divided by 2. And so, there's some tricks in there that you wouldn't sort of normally think of in first year calculus, but it's kind of a good workout, I guess. You could look at it that way. So I will go on to the next one here. And we didn't get a start on this one, I don't think. We talked about it being a trig substitution. The 1 plus x squared is the secant squared substitution, and taking the square root of that gives you secant. So what I've tried to do, I've circled all the ones over here that go back into the equation, okay? So we're going to replace the x to the fifth and times the square root, and then we're going to replace the dx with all of the things on the right-hand side. So that's how I arrive at this line, okay? So generally with trig, if you've got exponents on a trig function for an antiderivative, then the general rule of thumb is you want to get it down to an even exponent. So what they've done here with the tan to the 5, I've changed it to tan to the 4, and that takes out a tan, and then I've got the secant cubed. And then if you keep working it down so that now I've got tan squared, as soon as you can get a trig identity in there for like the Pythagorean identities, all the ones with the tan squared, cos squared, sine squared, then you can put the identities in and then things start to work out and you see, sort of where you're going with these. So that was the whole idea behind making it tan to the 4th, is that then I'm able to write it as tan squared times tan squared, and that's the important part there. So that's usually the goal when you're doing these, okay? So I'll let you have a look through this. When you get down to a certain point, you need to make another substitution, because when we're on this line here, it just is a little bit like there, you can't sort of integrate what you've got there. You might be able to simplify it a little bit, but you can't integrate it. But if you make this substitution, then you end up just with like a polynomial function, which you can use the addition rule for your integral there. Then it gets really tricky, and I don't know, I just don't think that any first year calculus student would be expected to know how to handle the bottom part of this using that secant of arctan identity. I think that's just going a little bit too far myself. But I put it in for you so you can see what to do with it, just out of curiosity. But honestly, I just don't expect anybody to think of that like in a test or a quiz situation. So that one seems like a little brutal to me. All right, let's go on to the next one. Okay, this was the sine to the 5th, and again, the goal for all the trig is to try and bring it down to even exponents of the sine. So the first time that we break off sort of a sine squared here, and then we leave the sine cubed, we're actually going to go back later with that sine cubed and break it down into a sine squared times a sine, but we won't do that all at once. So that's the idea. And then the sine squared from the Pythagorean identity becomes the 1 minus cos squared. And so if you work your way down here, by the time we change the second sine squared into the 1 minus cos squared identity, then we can FOIL that. That's what I get here when I FOIL it. And the sine x is the derivative of cos x. And so now I know that I've got a substitution situation here because I've got a function with the cos and its derivative with the sine both being in the integral. So that's what this substitution here is all about. And one thing to point out here is when you change your interval over from 0 to pi over 2, you'll notice that now the lower limit is 1 and the upper is 0. So there's two ways to handle that. You can just leave it like that and you end up substituting in 0 first and then the 1. Or if you want to flip it and put what looks like sort of a better order on it, you actually will make it negative when you do that. So you can handle that either way. I kind of like to just leave it as 1 to 0, and then it all works out when you're working it out in this line, okay? So if you follow your fractions through, then you should end up with 8/15, which seems way too simple for that one. Okay, and this last one with the arctan of x, if we use the substitution that u is going to be equal to the arctan of x, then du is the derivative of that. And so over here, the things that we're going to substitute in if we do an integration by parts, this is what we end up with. And so the tricky thing about this one, obviously, is we only see one term in here, one function. So if we make the other function a 1 so that we have two different functions to put into the integration by parts, that's how this one is going to work. And again, that's just nothing, I just can't imagine a first-year calculus student sort of thinking of those little tricks. These are tricks that come with like years and years of experience. So it's no wonder that people found these ones difficult to do. I'll let you read through the steps here. If you have any problems understanding any of it, just email me back. I've tried to write in little notes like to explain why ln of 1 is equal to 0. It's because that would mean e to the 1, e to the exponent something has to give us 1. And the only way that can happen is if the exponent is 0. And so I worked through all that for you there. And I'm going to be sending you something later because this video is already crazy long about the reduction formula. But this is probably enough to keep you busy on a snowy Saturday. Okay, thanks, bye.